Hello, welcome everyone to today's Journal Club session. Today we have our formal student, Dr. Biswajit Datta, who completed his BSc from Jadavpur University and took his MSc degree from IIT Bombay. And he pursued his long-term academic career, his so-called PhD degree from under the supervision of Professor Mandar Deshmukh. He's worked on a electron transport on a low-dimension system like graphene, and that work took him a Best Thesis Award. And he also done his first postdoc in Santa Barbara. Now he's pursuing his second postdoc in City College of New York. If Bishweda ready, then stage is yours, Bishweda. Today his title of his talk, as you can see, is this Polariton on MoS2. All yours, Bishweda.
Thank you, Surajit. Thank you for arranging this. So let's start. Hey, can you guys see my screen? I see. Can you see now? Not yet?
Not yet. It's just a white screen, Bishweda.
Okay, let me try again. Yeah, right. So do I share your entire screen or the window? Second.
Entire screen.
Okay. Now, is it visible? Visible? Okay, good. It's good? All right, let's start. Yeah, so I'll briefly talk about what I have been working for almost a year. So my current group focuses on something called Polariton, and I'll spend the first part explaining what is a Polariton, because this stuff was new to me as well. So I will sort of build up. So it's very easy to understand, and I'll keep things simple. Otherwise, you'll find out how much I know. Okay, so what is a polariton? So in condensed matter, we always use a notion of quasi particles, right? So quasi particle is basically dressed particles. For example, in solids, we talk about electrons are holes, which are different from isolated electrons, because their masses are different, right? In superconductors, we use Bogoliubov quasi-particles. So similarly, I'm going to introduce you today a new kind of quasi-particle, which you probably may not have come across so far. Now, so what are polaritons? Polaritons are basically half light and half matter type of particle, if you call it so. Now, we have studied the wave duality principle, right? That sometimes particles behaves as waves, sometimes waves behave as particle, but this is not what I'm talking about. This is literally, you take light and you take a material excitation, matter, and hybridize them. Now, this sounds very exciting, and I'll explain you how experimentally you can do all this. But the basic idea is this. You start with a matter, and you want to hybridize a material resonance with light. So you need a material which absorbs light to begin with. So when it absorbs under suitable condition, the light and the matter can hybridize. So so they need to have same energy, and after they hybridize, that will give rise to different states. One is lower compared to the original energy, known as lower polariton branch, and the other with higher energy compared to the original energy, that's known as upper polariton. Now, this material resonance that we talked about can be anything as long as it absorbs light. So it can be, for example, excitons in semiconductors. So in semiconductors, you have these states which lie in the band gap. So those are called excitons. They are basically bound states of electrons and holes. They can absorb light. So your material absorption can be exciton. It can be other things. For example, charge oscillations, lattice vibrations, which are phonons. It can be many things. In our work, we will have exciton. Now, to host exciton, you need a material, right? Where we'll have electrons and holes, and they will be as a bound pair. So any semiconductor will have exciton. For example, this gallium arsenide, regular 3,5 semiconductor. But no, that's not enough. In order to interact light with matter in a strong manner, you need to confine the light. And how do you confine light? You can confine light if you put light in between 2 meters. Then the light will, bounce back and forth a lot of time before the photon is lost. And that will buy the photon enough time to interact with the exciton strongly enough that we'll see it in experiment. Now, you know that photons in free space, it has linear dispersion, right? But that's not the case when you put it inside a cavity in between 2 meters. Because of confinement, it has the cavity has a certain mass. So this is basically the dispersion. This parabola you see is the dispersion of cavity. Now it's at higher k, it's like free space omega equals to ck. But as you go to small k, it develops a mass, and it differs from the usual linear dispersion. And we know that the curvature tells us about the effective mass, right? And in this picture, the exciton looks very flat. And the reason is that exciton being a bound pair of electrons and holes have much higher mass. So that means in the K region where it's plotted, the exciton is basically flat. It's very heavy compared to the photon. So photon in free space supposed to be massless. However, in a cavity, the cavity has a certain mass. That's why it has very high dispersion. So this is what we are talking about. Now, you can see that at these 2 locations in the K space, they become degenerate, right? The cavity you have to design such a way that that they become degenerate at some K. And when they become degenerate, under suitable condition, they interact strongly and will give you 2 new eigenmodes of this system, the upper mode and the lower mode. Now, why is polariton interesting? Now you can think that you have got a quasi particle which is half light and half matter. Now, for your experiment, you can have all the good properties of light and also all the good properties of material excitation. Now, what are the good properties? Good properties of light is light has very small mass. I mean, in free space, it has no mass, but in cavity, it has small mass. So the new quasi particle you have will be extremely light. So it's easy to move them around, but also, but the problem with light is you cannot control it, right? So you for example, it doesn't respond to gate voltage, electric field. However, being a quasi-particle of light and matter, this will inherit those properties from the excitonic part. Now, they might be tunable with a gate voltage and all sorts of those stuff. They can be, there is a property called non-linearity. Basically, it means when you shine with a lot of laser power, they can interact, the excitons can interact. One thing with light is they don't interact with each other. So that is the, so if you want a device where you want things to interact with each other, then light is not a good choice. But here, being half of the part is excitonic, you can have that property, so which is good. Now, as I said, the material part can be any type of material excitation. If you are focusing on excitons, even in excitons, different material can host excitons. You can have 3D material, you can have 2D material, but in our lab, we are focusing on 2D materials. These are called transition metal dichalcogenides, many of you know. And what are the advantages for them to use as polariton basis? First of all, so being a bound state of electrons and holes, they have a particular binding energy, right? For traditional T5 semiconductors, the binding energies are typically very small, like a couple of MeV or even fractions of MeV. So that means you necessarily have to do all the temperatures in Kelvin, millikelvin regime. However, the binding energy of 2D semiconductors are very high. It's like it can reach even of the order of EV. So that means you can do all these experiments at much higher temperature. Also with TMD, you already know that, many of you know that they have something called valley property. So it comes from their crystal structure. They have a hexagonal crystal structure. And because of the crystal structure, in the K space, they have valleys. Now these valleys are addressable with a particular polarization. So in experiment, now that's a very good knob that you have. You can come up with left circularly polarized light or right circularly polarized light, and you can excite one valley over the other preferentially. So that's a good knob in experiment to have. Now, being the quasi-particle of light and matter, light and exciton in this case, and the polaritons also retain that property. So that is good. Also, these excitons. So excitons, as far as practically concerned, they are like atoms. With, for example, in atoms you have different energy states, right? So for excitons also you have different energy states. So 1s, 2s, 3s. But that binding energy reduces as you go to higher state. But those are interesting also. And to begin with, since the binding energy is pretty high, the binding energy doesn't reduce as quickly for even higher states. So you can study those also, which are not possible in the traditional 3-5 semiconductors. And there is something called large oscillator strength. So for practical understanding, what oscillator strength means is how strongly the material absorbs light. So the stronger it absorbs, the stronger it interacts with the light. So you'll have better polariton. So turns out these TMDs, even they're extremely thin, they're very efficient in absorbing light. So it's good for producing polaritons. There are also other charged species in TMDs. For example, exciton is a bound pair of electrons and holes, but you can also have tryons, which are, let's say, 2 electrons, 1 hole, or 1 electron, 2 holes. You can also couple them with cavity. But in our talk, we're gonna focus on this property. It's called non-linear property. So what it means is when you when you have polaritons, right? So polaritons are itself a hybridization between excitons and light. Now, usually these polaritons, they can have interaction between them because that interactive property they have borrowed from the excitonic part. Now, for device applications, you want things to be nonlinear. For example, in transistor, right? Things are nonlinear. So here also for device applications, so nonlinearity is a property which you want. And so traditionally, so how do you increase nonlinearity? So you have to shine a lot of laser power, which will create a lot of excitons. And those excitons will interact with each other more and will give you nonlinear energy shift. So this is what we want. But traditionally, it has been shown for very high laser power. So we want to show non-linearity at laser power, at lower laser power, so that it's manageable and in a lab environment. So again, why is the non-linearity property interesting? So some of you may relate it to something called Coulomb Blockade. Whoever have studied nanoelectronics a little bit. So there's a concept called Coulomb Blockade. So what happens is you design the system such a way that when you populate the system with a single electron and with a double electron, the energies are not linear. So there's an energy penalty you give when you populate the second electron. So the electrons interact. And here also, the idea is, let's say you have a system and the system absorbs one photon. So the energy rises from here to here. And then you shine another photon. And so the system has two photons now. So if this was a linear system and the two excitations don't talk to each other, then the energy will increase to here. But that's not the case. You want the system to be interacting. So the two polaritons should talk to each other. And this is the energy penalty. So the system is not linear anymore. It's a non-linear ladder. Why is it interesting? So now, since there's an energy penalty, you can have one photon absorb at a time. And if you have one photon absorb at a time, the system can also emit one photon at a time. And this is something called single photon emitter. There's a measurement called G2 measurement where you can find out if your emitter is is emitting one photon at a time or not. So if this G2 reduces less than 1, then if it goes to, so the lower it is, the better single photon emitting system you have. So in literature, it has been shown a little bit reduction compared to 1. So it's going in the right direction. So now we are interested in polariton-polariton interaction. And so what are the mechanisms by which these polaritons can interact? So it turns out that in real systems, you usually have two kinds of mechanism playing simultaneously. So let's start with an exciton mode and a cavity mode. Where they cross, you will have two new modes of the system. This is upper polariton and this is lower polariton. Now, what you do is you increase the laser power, and the increasing laser power produces more number of excitons, and they interact with each other. So in one kind of interaction, you can have the exciton energy itself shifting. So it turns out the effective interaction between two polaritons are usually repulsive. So under repulsive, you have when you are packing with higher number of polaritons, the energy increases, right? And since now the exciton increases in energy, the resultant upper polariton and lower polariton also increase in energy. But you can have another type of effect. This is called phase-space filling. Forget about the term. And this comes because polaritons are made of excitons and light, right? But the excitons are also not point particles. So excitons are bosons, because it's a bound pair of electrons and holes. However, it's not a point particle, right? It's a composite particle. Now, what happens when you increase the power and pack many polaritons close by? So they start seeing the internal structure, and they start annihilating. And once they start annihilating, they will produce electron holes, and that will give a background density of plasma. And this plasma reduces the oscillator strength. What is oscillator strength? How highly it absorbs, how highly the material absorbs. Now, if the absorption goes down because of this background plasma, then the interaction of the exciton with the light will go down. And what will happen is this splitting is a measure of how strongly it's interacting, right? So the splitting will go down. So under this effect, the upper branch will red shift and the lower branch will blue shift. So experimentally, you can find out what is happening in your system. Are both the branches blue shifting, or both the branches red shifting? And in real experiment, you can indeed have a combination of two. Okay, so now let's look for a system where the excitons interact with each other better than other systems. So what do you need in a system, in an ideal system? So recently there is a report where they take two different TMDs, MoS2 and WSE2. They stack with each other. And what happens is, if you see the band structure, so this is a carton, this is the conduction band, and this is the valence band. And their energies are such that their band alignments, it's called type 2 band alignment. Again, it's just a jargon. What it means is the conduction band, if you see, MoSE2 is lower, and for WSE2, the valence band is here. So all the electrons of this heterostructure gets transferred here, and all the holes get transferred here. So so what happens is now electrons and holes are separated in two layers, right? Electrons are in MoSE2 layer and holes are in WSE2 layer. So because of that, you generate a dipole moment perpendicular to the layers. And dipole moment is good as long as the interaction is concerned, because apart from regular interaction, you have dipole-dipole interaction, and the interaction increases, and hence you can have better non-linearity. So this is a PL photoluminescence from their heterostructure, and these are the regular PL, and this is the PL that they're looking at, which is a signature that this has happened. This is the exciton. The holes are in one layer, electrons are in one layer, and they are now bound in terms of an exciton, and that shows up in a photoluminescence measurement. In terms of experiment, what they do is, since this is a permanent dipole moment, and you know that dipole moment, the energy of dipole moment can be tuned with an electric field. Now you can have this device in a FET geometry, right? Basically a capacitor geometry, and you can produce electric field to tune the energy of this dipole. But in terms of the nonlinear measurement, so this says that you indeed have a permanent dipole. The exciton possesses a permanent dipole moment. That's why it can be tuned. Now, in terms of experiment, what you see is the authors claim that the low power, you see two peaks, and they claim that this second peak is the emission from this system when the system absorbs one photon. As you increase power, the system absorbs more photons and goes to this state. And you see that if the two excitons interact with each other, then this will not be this difference will not be same as this difference. There will be an energy penalty which will come from exciton-exciton interaction. So this peak will be shifted different from this. That's what they show. So that's what they claim, that they are indeed in this limit, that the excitons are, even the single excitons are talking to each other. But there's one problem with this system for the polariton study, because you remember for polaritons, since it's a hybrid particle of light and matter, so in order to produce polariton in the first place, the material need to absorb light. However, right here there's a problem. As I told you that here, look at the dipole orientation. The dipole is perpendicular to the layer because the electrons and holes are completely separated into two different layers. And in typical experiment, you shine in laser from top. When you shine in laser, so the K vector is perpendicular to layers. So the electric field is perpendicular to the K vector, right? So the electric field is oriented in plane. However, the dipole direction is out of plane. So they are not going to couple. You know that energy of a dipole due to electric field, right? It's P dot E. So if they are perpendicular to each other, cos 90 is 0. So you will not have any coupling. So what that means is if you shine light, this dipole, this excitons, because of their wrong dipole moment alignment, it's not going to absorb. If it's not going to absorb, you're not going to have polaritons. So this is not a good system for polariton study. What else can you do? So there are some progresses in traditional 3-5 semiconductors, for example, in gallium arsenide in this system and indium gallium arsenide. So what you have in this system is these are MB grown layers of gallium arsenide and indium gallium arsenide. So you have two quantum wells, right? Where you have electrons, one quantum well supports electron, another quantum well supports holes. Now you can again make the device such a way it's a parallel plate capacitor, and you can produce a little bit of electric field. What that does is it sets up a preferential direction for the electron to tunnel a little bit on the other quantum well, because you have electric field, right? And so what that does is that also generates a little bit of electrons here. And so in the end, you have a dipole moment both perpendicular to the layers and a dipole moment parallel to the layers. So you have two kinds of excitons. Now in experiment, what they show is, so remember which one will be tunable by an electric field. The vertical dipole will be tunable by the electric field, because this dipole is parallel to the electric field. And you can tune the electric field. So these are, this is one and this is another, and where they cross, and so where the one exciton crosses the other, they will hybridize and give rise to new excitons. And now you can put this system inside a cavity where you have a cavity mode, and they will again hybridize and give rise to a new mode. So forget about the details. The take-home message is what you are trying to do here. You remember in the last system, you had vertical dipoles, which was very strongly interacting to each other. But the problem was because of wrong dipole moment orientation, it does not absorb. So you want the property, you want that property, but you also want the property that it absorbs light. So in order to absorb light, the part of the dipole moment should be aligned in plane. And that's what they're trying to do here. They have two different dipoles of two different orientations. When they overlap, the resultant dipole has both these properties. And now it's good. Now it can absorb light. So now you hybridize with light, form a polariton. and that's what they show. And how do you, by the way, how do you show that in experiment your polariton is strongly interacting? Again, you shine it, shine with laser, you increase the power, and when you increase the laser power, you increase the number of excitons and number of polaritons. When you increase the number of polaritons, they start interacting closely, and because of the interaction, repulsive interaction, their energy shifts. So you have a blue shift, and that's what you look at in experiment. And of course, they can tune with gate voltage, so that's good. But again, all these experiments have to be done at very low temperature. Yeah. Now here TMD comes, that we want this sort of good things, but at higher temperature. What do you do? And also in much, by the way, the reason 2D materials are very famous is that not only you can do things at higher temperature, it's also because of its simplicity. And that's a big deal, because all this experiment I talked about in the last experiment, all this, in order to do that, you need a fancy MB machine, which is probably the most expensive machine in a condensed matter lab. It's crazy expensive. So 2D material is a great system for that, because you don't need MB. You just stack different materials and do this experiment at dirt cheap cost. So that's why we're interested, and that's why this field is thriving. So what happens in a bilayer MoS2? So in bilayer MoS2, it turns out you have a particular excitons, which is known as interlayer excitons. So that means if you look at the electrons and holes, the charge distribution is kind of weird. The electron is localized in one layer, however, the hole is delocalized between two layers. Now, if you see, because of this weird charge distribution, you have a vertical dipole moment and you have an in-plane dipole moment as well. Now, that's very nice, because it instantly inherits both the property that I talked about. It can be tuned with a gate voltage. Because of the vertical dipole moment, it also interacts strongly compared to a regular exciton. And because of this in-plane dipole moment, it also absorbs light. And that's what is shown here in this paper. You can see that this is the regular exciton, and this is the interlayer exciton that is of interest to us. Because this interlayer excitons, in principle, we should be able to couple with a cavity because of right dipole orientation. Now, they also show that because it has a permanent dipole moment, you should be able to tune it with an electric field if you make a FET device. And this is just a fancy color map of that. You have three excitons. The y-axis is energy, the x-axis is electric field. So you can crank up the electric field in the x-axis, and you see that the energy of this guy, these two excitons, they don't change much. Again, why do they not change much? Because their dipole orientations are in the plane, and your electric field is out of plane. So with an out of plane electric field, you can only change the energy of an out of plane dipole moment, which is this interlayer. You can see that as you can increase the electric field, their energy becomes so the non-degenerate, and it breaks into two, all this stuff. But for our experiment, the take-home message is this is a good system for cavity measurement for forming polaritons, because of their convenient in-plane and out-of-plane dipole moment. So what do? Yeah. Okay. So so those are details, but This device would be complicated, but let's not get in the application, the complication. But to answer your question, you can design a system nicely. For example, what you can do is you can choose graphene also, right, which is transparent. You can get the device, light will also go through. In certain experiment, you can also choose a thin layer of metal, and that came as a surprise to me as well, that thin layer of metals can easily let light pass, and that is enough for forming polaritons. For example, if you choose 20, 30 nanometer, even 40 nanometer metal, enough light will pass for you to work with the device. Any metal, but there are again there are complications which these okay, yeah, these are very well studied in tons of, so there are like standard softwares even, unlike the nanoelectronics community. Turns out this community, they use all standard Maxwell equations, right? And so there are softwares which implement Maxwell equations in different format, and you can calculate all this. That's not a problem, but you can also experimentally measure it. All right, so what you do, you first find out whether you have MoS2 bilayer or not, right? And how do you do it? The one way to do is to do reflection measurement. So you shine white light on a MoS2 flake, and so they have band gap, right? So it's a semiconductor. So once the light has higher energy than the band gap, everything, I mean, a lot of the light gets absorbed. But in the band gap, you have excitons, right? So in monolayer MoS2, you have two excitons, A and B excitons. So they are the one which have in-plane dipole orientations, right? So they absorb. So you see two peaks. So these are in-gap states. They exist inside the band gap. In bilayer MoS2, on the other hand, you have these two excitons. In addition, you have a new exciton. This is the interlayer accident, and very conveniently, it shows up even at room temperature. So that's very good, because you can then do these experiments at relatively higher temperature. And this is the signature of bilayer MoS2, that you have this interlayer excitons. And this is what we are interested in. Now, what we do is we take this bilayer MoS2, put it inside a cavity. So this cavity, in our experiment, is made up of 2 meters, basically, right? So you need 2 meters to form a cavity. The top cavity, the top part is basically a thin layer of silver. The bottom one is something called a DBR. It's not a metal reflector, it's a DBR. It's basically an alternative layers of different insulators. In our case, it's SiO2 and TiO2, and turns out the thickness is chosen such that they reflect in a way that if you have sufficient period, you have almost 99.99% reflection from the structure. So this is another type of mirror, which is not made out of metal. And there's a particular reason to choose that over metallic mirror, because of its low loss. Again, I'm not going into those details. That's just how you should design the device. So the bottom line is you have this MoS2 in between these 2 mirrors, and you shine in light from the top vertically. And when you shine light, remember this MoS2, for interlayer excitons, you have a dipole moment like that. Part of the dipole moment is this oriented in plane, and part of the dipole moment is oriented out of plane. Now the in-plane one couples to the light, and the out of plane one should give rise to higher nonlinearity, higher interaction. So in experiment, what we see, in experiment, this is something called Fourier Imaging. Again, I'm not going into the details, where you can basically map out the band structure in experiment. So you plot energy as a function of in-plane momentum, which you can also express in terms of theta. Theta being, if you have momentum k vector, you can have k cos theta, k sin theta, right? So that theta. So it's the in-plane momentum. So you see different branches, like in regular solids. You see here also, you see a band structure. You see different branches. For example, what happened? Okay, yeah. So we see different excitons getting coupled. So here you have one exciton, here you have another exciton, here. So you have 4 excitons in total, and all of them get coupled to the same cavity mode. So your cavity is like that, a parabola here, and all these excitons are like a straight line, and they get coupled and give rise to this sort of a band structure. And how do we measure it? Again, we take the reflection, we shine in a regular white light, or it could be a white laser, and then because we need a continuous energy, so you can shine in white light and measure the reflection from the structure. Wherever there is a mode involved, the light will get absorbed, and that will show up as a dark line. That's how you see the band structure. Now, this system can be described in terms of a 5x5 matrix, where you basically have, remember, this matrix is nothing but it's a mathematical way to. So this does not care about any quantum mechanics. So this is a quantum mechanical system. However, this matrix is very dumb. It's nothing quantum goes here. It's just a way to model it. So you just have a cavity mode, which is like a parabola, and that couples with all other different excitons, which are like straight lines. And you have a certain off-diagonal term which says, how strong is the coupling between the cavity with that particular exciton. It's just a 5x5 matrix. You can treat these things as fitting parameter and try to fit with the experimental data. When you do that, that gives you the splitting of these modes, which you can now quantify and study them as a function of different things like laser power and stuff. And that also gives you the precise locations of these excitons. So we can fit our data very well, and we can study it. So you can take line cuts at different angles. So what do you expect? Let's focus on this bottom 2 branches here. You take a line cut here at 0 angle. You remember this is the location of A excitons. So in terms of energy scale, now we are plotting reflection as a function of energy. And we are taking a line cut at 0 angle. So in this direction. So you'll see that, so you come across 2 dark spots, right? So you're gonna see 2 dips in experiment. So here, had there been any cavity, had there been no cavity, you would see A exciton right here. Now, when you have cavity, remember what cavity does. When the cavity mode is here, it strongly interacts with the exciton. And as a result, you have 2 new eigenmodes of the system, right? So you see, instead of the dip being here, you have a new dip at lower energy and you have a new dip at higher energy. So those are 2 branches of the polaritons. The same phenomena you will see at different layers, different angles, because they intersect the cavity mode at different angles. So for example, if you take a line cut here, this will show you what happens to the interlayer exciton. You see, again, the interlayer exciton breaks into two polariton modes, similarly with other excitons. So and now we have formed polaritons. Now this itself is a big deal, because you consider the simplicity of the experiment compared to the last one, where you had to do all this complicated measurement. You have to have two quantum wells, and then precise control of our electric field, so then you can tunnel a little bit of electrons to the other layer, form two different kinds of excitons, hybridize them, and then hybridize with cavity to form this. But here, the very nice property of the interlayer exciton is such that it has two kinds of dipole moments, and to begin with, doing nothing, you can couple it with light. Now in experiment, what you do to study the nonlinearity is, again, you crank up the power. So these are just line slices taken here. So these two dips are these two dips of the interlayer polaritons. And zoomed in here, this two dips. You increase the laser power, and hence you increase the number of polaritons in the system, and they start interacting. And you see here the gap sort of closes slowly. So the two branches come close. But if you take a line slice at slightly different angle, you see that both the branches sort of blue shifts there. So as I said before, depending on what mechanism is in play, you can have two branches of the polaritons coming close to each other, or you can have both the branches to blue shift. Now you can study that, all this, and you can quantify the nonlinearity. So this is what is happening in our system. If you look at small angle, the branches come close to each other. At a higher angle, both of them blue shift. Now, to quantify it, how do you quantify it? So I'll not go into the details of this to bore you guys, but you can come up with some numbers. So what you do is basically you look at the branches, how fast they are blue shifting with respect to the number of polaritons. And then you can fit it with a straight line, and the slope of the lines tells you how strongly the polaritons are interacting with each other. So now remember, we have different polaritons, right? And this polariton interlayer, they have permanent dipole moment. So we expect them to interact stronger than a regular exciton. So we can produce a similar curve for a regular A exciton, and we see that as per expectation, the slope is indeed much lower. So what do they mean? What do these numbers mean physically? So the mean says, so if you take a line cut at each of this absorption, you'll have a line width of the absorption, right? So in our case, it's the line width of this mode right here is around 15 MeV. So so if you divide this line width by this slope, you get a number, and that is the number that you need, that many polaritons you need to shift by one line width. So that tells you how strongly your system is interacting. For example, for the interlayer, you only need 38 polaritons, roughly 40 polaritons per micrometer square, for the branch to shift one line width. Now, if you do the same analysis for the A polaritons, it turns out you need 520 polaritons to shift by one line width. That means this system is much more strongly interacting by a factor 518 by 38. So that is what we expected, and that is what we see. Now you can further go ahead and find out, what kind of, now you know that your system is nonlinear, your system is strongly interacting. What effect is playing a role? Is it exciton-exciton interaction, where both the branch shifts, blue shifts, or is the other one where you have phase space filling, where both the branches shift in opposite direction? You can quantify that. I'm not going to go to that details again to bore you. And in our system, we find that we have indeed a combination of two. However, the saturation is dominated. Yeah, with that, I'd like to conclude. So we have seen that the interlayer excitons in bilayer MoS2 is a great platform to study nonlinear polaritons because it has permanent dipole moments, and it can be further tuned with gate voltage. The good thing is, fabrication wise, it's very simple to make compared to the 3.5 semiconductors. And also, still we are not at the Polariton blockade regime. Remember in the beginning I told about Polariton blockade, where you need the system to be sensitive in a single photon regime or single Polariton regime. However, our numbers are still in 40s, so it still needs to be improved by order of magnitude, and there are several ways to go about it in future. Yeah, with that, I'll conclude here, and thank you for your attention. Hello? Yeah. Yeah, please.
Hi, Biswajit.
Hi.
Can I ask a question?
Of course.
Okay, so you said that the dipole moment of the interlayer exciton is oriented out of plane, and that's why the interaction with light is lower compared to the.
For interlayer you have both a component actually, so that's why.
Yeah, in case of MoS2, I understood. But what about the in-plane excitons? So do they very strongly interact with light? And so, I mean, in your device so far, I found that you are not applying any electric field.
Exactly.
But then for the in-plane exciton, you should see a higher non-linearity, right? Because they are going to interact more strongly with light.
Okay, so there are two things, right?
Yeah.
So there are two kind of interaction we are talking about, right? So one is the interaction to form the polariton itself, right? Because being a quasi particle of half light and half matter, you need the exciton to interact with the cavity to begin with highly enough to form the polariton, right? So this is one type of interaction. But the kind of interaction that I am talking about here, once you form the polariton, how strongly the polaritons are interacting with themselves. So that's a different excitons. Sorry, that's a different kind of interaction. So in terms of physics, the first is basically single particle interaction, which can be captured in this Hamiltonian. Where is it? Here, right? Sorry. Here. So this is just a matrix, right? Now, for example, consider this A exciton you are talking about, intralayer exciton. Now, it has a certain off-diagonal term. So if you increase this off-diagonal term, what will happen is the splitting will increase. So that means this exciton is interacting more strongly with the cavity. But this is single particle. This is not what we are talking about. We are talking what is the interaction between two polaritons, not with the exciton and cavity. So that can be increased if the polaritons have a permanent dipole moment. Now, where do the polaritons inherit this dipole moment from? They inherit from the excitons. And for interlayer, you have a permanent dipole moment because of this charge distribution, right?
Yeah.
So you have a vertical dipole moment, and because of this permanent vertical dipole moment, they interact with each other stronger than a regular A exciton. Because for A exciton, if I have to draw a similar diagram, then I'll have electron here, hole here. So no out of plane particle dipole moment. So hence the interaction between two polaritons are poor, and that shows up in the number here.
Yeah, but do you mean that only the vertical dipole moment will give rise to stronger interactions?
Oh, that's just because, yeah, I understand. Right, I understand your point. That's just because when you have in-plane dipole moment, right, they don't have a preferential dipole direction. So we call it oscillating dipole moment. So they don't, so they are in plane. However, on an average, the time average is 0 because it can be oriented in any direction. So it doesn't contribute to the interaction much. However, for the interlayer, it's not a function of time, right? It's just out of plane. So their contribution is much more. And that shows up in the number. This is for it.
So it also has something to do with the longer lifetime of the interlayer excitons then, because then they on an average they have a more permanent dipole moment, while the in-plane excitons, which are shorter lived, would be, does it have to do has anything to do with the longer lifetime or not?
Yeah, that's true that they should have very different lifetime, because in one case you have electrons and holes separated in different layers, and in the other case you have on the same layer. However, for this purpose, my primary reasoning is that for intralayer, time average dipole moment is 0 because it's oscillating. But for interlayer, there is a static dipole moment. Not sure if it has something to do with the lifetime.
It is also kind of longer lived, right?
Yeah, that's true. That's true.
And it has more time to interact with light in that sense somehow.
Yes, it's possible. Yes, I agree.
Okay, thank you very much.
Sure. Oh, oh, you mean okay. Oh, where the polaritons are. Okay. So you think that's a hard question. You think about it. So it's like half light and half matter, right? So what it means physically? What it means physically is you have a photon inside a cavity, right? And because of these two mirrors, the photon is constantly going back and forth before it leaks out of the cavity. And what we are calling polaritons is this physical process that the same photon is getting absorbed by the material multiple times. It's getting absorbed, emitted, again absorbed, again emitted. So it can do this cycle a reasonable number of time before the photon is lost. That is what the polariton means. So it, however, the exciton, as you can think, it's hosted by the material itself, right? However, the photon exists. When it's absorbed in the material, it's there, it's lost, and then when it's emitted, it's again in the cavity, in the entire cavity, right? So where is the polariton? It's in the entire cavity. So right, like the exciton. Yeah, for example. Mhm. I'm not sure if it's the same. That's a good question, and I'm going I'm I'm going in a limb here because I'm not sure about it. For example, I'm comfortable talking about the wave function of the exciton, the spatial extent of it, right? So because you can plot it, and you will see that for intralayer for A and B, it should be in one layer over the other, and for interlayer, you would see that the wave function will sort of half on the one layer and some part on the other layer. But for Fullerton, it's probably possible. It's just that I don't know how would the wave function look like. I would guess that it should exist outside as well because it's half light, half matter. Oh, yeah. Yeah, no. I did not. I did not tell you how to do that in experiment. Um, there are many ways to do it. So there's a concept of Fourier imaging in optics. So I don't know how to explain it simply, but you basically put a couple of lenses, and in one case, it turns out that you image the K space the way we do here. So you basically have a circle. That circle is basically, if you talk about band structure, if you take a slice of the band structure, you get a Fermi surface, right? That sort of thing. So you get a Fermi surface type of thing, and then you cut it along one direction, you see this. So it's all with lenses. Yeah. Exactly. The good thing about this is optics in many cases happens in parallel. So unlike our electrical measurements, right, where we acquire the data in series, right? We tune in a particular whatever density, whatever some field, and you gather the data. Here, things happen in parallel. That's why it's so fast. So you shine in light, and you grab the data in one snapshot. That's all. It takes 20 seconds, 30 seconds. Here, there. Oh, this guy. Oh, okay, yeah. Okay, these are artifacts. These are artifacts. For example, where you're shining the laser. If you have some inhomogeneity, right, then you can have a little bit of excitant shifted elsewhere. Also, it can be from your setup itself. If the setup has some dart or something, you can have this. This is, and you see these lines also. No. This one is taken at 7 Kelvin, but these are easily visible at higher temperature. For example, I do not have the data here, which is taken at 77 Kelvin. You can perfectly see it. Yeah, right. Cause the like free electrons and holes, like we studied today, these excitons are also sensitive to magnetic field. They have a G factor. So once you apply, and they can have G factor negative to positive, all kinds. So depending on the magnetic field, they will further split. Yes. No. We don't have any relation with magnet in our lab. No magnet exists.
Okay. Hi, Biswajit. May I ask another question?
Yeah, sure.
About this, the excited state of the A exciton. So, the excited in some of the theory papers that I came across some time ago, they also show that the excited state is perhaps more delocalized out of plane than the A exciton,
Oh
than the
yes,
ground state of the
the
A
the,
exciton.
the 2s of exciton you're saying, right?
Yeah, yeah.
Yeah.
So, do you also see a stronger polariton interaction for the A2S than the AX?
Yeah. So yeah, so actually turns out we had a former student who actually studied this,
Right.
the 2s state in WS2, I believe, and
Mhm.
where he indeed shows, I don't know, factor of, I forgot the number, it's like factor of 5 higher or something. And that's why I did not study this. In our case, even though we see similar, you see this similar
Yeah.
strong coupling here. This is actually 2s of A,
Yeah.
but yeah, I haven't studied that because it's already studied and it's known that it's likely to give higher numbers. We are
Mhm.
primarily focusing on the interlayer here.
Okay. Thank you. Very nice talk, by the way.
Yeah, thank you.
Vishwajit, can I ask one small question?
Yeah, sure.
Yeah, so I am new to this idea, so I have one basic question. So as
Me
you
too,
said
me
that,
too.
yeah, okay. So as you said that polariton is the hybrid mode of exciton and photon. So then you
Hmm.
showed this dispersion relation. So there the excitonic dispersion relation is k independent. So can you say something more? Sorry, I missed that part.
Okay, okay. So let's go here. So remember when things have dispersion, right? So dispersion is a measure of mass, right? Effective mass.
Yeah.
Um, so the cavity, which is
Hmm.
basically light, should have the maximum dispersion, right? Because it has the lightest mass possible. So
Yeah.
it disperses a lot. And exciton, on the other hand, is a bound pair between an electron and hole, and they are massive particles.
Okay.
So in this K regime where I have plotted, the
Hmm.
exciton almost has negligible dispersion. If you of course go to very high K, the exciton will also start dispersing, but not in this regime. So now here, um, the resultant two modes are, hybridization between these two, and so they have dispersion because the light has dispersion.
Acha, okay. Biswajit, one small question is so the line width or the Q factor of these modes, how they depend on temperature. So, for example, versus 7 Kelvin versus room temperature. How it is.
Yeah, good, right. So the Q factor. So as you see the polariton, right? So if we talk about polariton, so it's a hybrid between light and matter, right?
Hmm.
So the Q factor will have two contribution, right, from light and matter.
Right.
Now, in terms of the cavity is almost independent of light because nothing is temperature dependent happening here, right? It's just a two piece of mirror, right, where the light is going
Right.
back and forth.
Yeah.
So nothing is temperature dependent. However, the exciton is strongly temperature dependent. So at room temperature, you have all sorts of broadening here. And as you go to lower temperature, your key factor increases, lower broadening. So
Right.
the polariton also, for polariton, the Q factor will be more at lower temperature.
So, but like typically, like how much increase it goes through?
Oh,
Do you have any
okay.
number
These
like
Q
rough?
factors, these Q
Huh.
factors are very small. We are talking about, okay. This is not
Oh.
your device Q factor. These are very small Q we are talking about. because we are talking about feasible reaching. So these Q factors are something like 200, 300 we are talking about.
Okay.
It's much smaller than your
And
devices.
that will have some dependence from the, as you said, like you can use laser also and white light also.
No.
So in that
It's-
sense, will it depend or?
It doesn't depend much on that. It's mainly the
Okay.
cavity.
Okay. Oh, you are saying that basically the cavity itself will determine what will be the Q of the light, for example, right?
Yes.
Okay. That
Cavity,
will not
yes.
have anything to do with laser versus normal light, you are saying.
Mm.
Okay. Okay, fine. Yeah.
Actually, another small question. Sorry.
Yeah.
So as you said that the in-plane excitons they couple more to light.
Hmm.
Can you explain that?
Yeah. So let's see. How do we shine light? Let's take this. Okay. You see this light we shine perpendicular to the mirror. So along KZ, right?
Right.
And so the light is propagating in this direction. So where is the electric field oriented? The electric field is along this plane, right?
Okay, perpendicular.
Because case perpendicularly.
Mm-hmm.
So and you know that the energy of a dipole moment is P dot E, right?
Mm-hmm.
P is a dipole moment, E is the electric field. Right. So you need the dipole moment in plane in order to couple it. If it's perpendicular, then it's cos 90, 0. So pure out of plane dipole moment will not couple at all.
Okay. And another small question that these excitons, these exist in semiconductors only, and I mean, what is the condition that one will get this exciton? Just have band gap material, or?
Yeah, exactly. You just need to have band gap. There are other things. The primary thing is because the excitons by definition, it's an in-gap state. So graphene you won't have it unless you have. You can have it in bilayer graphene. You basically produce electric field. Yeah, you can have it, but you need a gap state.
Okay, fine. And is there any energy scale relevant for this process? So, for the cavity mode, you have some distortion in some energy range.
Right.
That they will hybridize.
Yeah. So it's set by the exciton itself. I might have an exciton here. I might have an exciton way up in energy. So I have to design my cavity such that it becomes degenerate at some point with the exciton. Okay.
So actually, you have many excitons. Only where the cavity mode crosses, you have the polariton.
Exactly.
Okay.